everyone. Thank you so much for joining us today for a very special guest speaker session. We have with us Qinyuan Yi. Qinyuan recently completed her PhD in computer science at University of Southern California and is a research scientist at Salesforce Research. Her research centers on enabling NLP and AI systems to learn in a data efficient and productive manner, with an emphasis on meta learning. Today, she will be presenting her latest research on function induction and task generalization, an interpretability study with off by one edition. Thank you so much for taking out your time, and I'll hand it over to you.
Hi, everyone. Very excited to be here today. I'll be talking about our work on function induction and task generalization. And this is joint work with Robin and Xiang at USC. Let's get started. So I like to start with a very interesting internet meme. When ChatGPT was released about 3 years ago, people are obsessed with getting it to say 2 plus 2 equals 5. And you will see these Reddit posts that get viral at the time. People try really creative ways like repetitively convincing models that 2 plus 2 equals 5, or even saying that my grandma believes so, so you should agree with me, something like that. And some people get really serious about this, and they even wrote a research paper on this topic. And recently, I gave this a try myself, and interestingly, I found a solution that is different from all these mentioned in the previous slide. So what I'm trying here is I took a Llama 3 8 billion size model, and I used a simple prompt by saying that 1 plus 1 equals 3, and asked it what is 2 plus 2. And surprisingly, this model will spit out 5. It's very surprising. And I just decided to explore more into this direction. And later, I found out that 2 plus 2 equals 5 is not just one-shot outlier. This behavior was documented well in Big Bench, a collaborative benchmark effort a few years ago done by Google. And in this benchmark, there is one task that looks like this. Models are prompted with these wrong equations like 4 plus 1 equals 6, 5 plus 3 equals 9, and these models will be asked about what is 6 plus 2. And from now on, I will refer to this task as off by 1 addition, because we just add an additional 1 to the right-hand side of this equation. In Big Bench, people observed that very large language models like Palm's 64 billion size or 535 billion size models, they have non-trivial performance on this task. And also the accuracy increases as the model size grows larger. So this is also identified as an emergent ability in the emergent abilities paper. And that was the Big Bench effort a few years ago. So we tried more recent models. For example, models like 5.4, Llama 3, Mistral, those models that are more recent. And they also come from different companies. And what we find out here is that these more recent, smaller models can also perform this task really well. By giving them maybe 8-shot or 16-shot of in-context learning examples, these models have non-trivial performance. And 2 of the models, like 5.4 and Llama 3, they have near-perfect performance on this task. So all these observations suggest that this is a very general phenomenon present in many language models. And this leads to our question, how do language models achieve this? How are they able to infer that we want an additional 1 in these equations? So this talk and this research paper is designed to solve this question. And I also wanted to say that this is a very specific, limited application of language models. But perhaps I also wanted to take this chance to see if the result can get us closer to many other questions people care about. For example, people are always interested in context learning abilities of language models. So this off by one addition task is a really interesting counterfactual task. And maybe by investigating it, we can understand whether models can really learn unseen tasks within context learning. And maybe we can also help answer how language models handle misinformation in their prompt. For example, 1 + 1 = 3 can be seen as misinformation. And lastly, maybe investigating this will help us answer why certain emergent abilities emerge at certain model scale. So these are the goals, some of the goals, or maybe some of the questions I hope like our investigation into off by one addition can give us answer to. And to answer this question, how do language models perform off by one addition? We turn to some more recent interpretability tools that help us go deeper into model internals layer by layer to understand what the model is thinking internally. And in particular, we will be using the technique presented in these two papers. One is called activation patching, and the other one is called pass patching. These two methods will help us understand the activations within these language models. And if you're not familiar with these two papers, don't worry, I'll give a brief introduction in the next slide. So how these methods work goes like this. We will give a language model, for example, a Gemma 2 9B model, the main model investigated in our work. We will give it two prompts. On the left-hand side, we give it a prompt of standard addition, where everything is correct. You have 1 + 1 = 2, and you would expect the model to output 3 + 3 = 6. But on the right-hand side, we will give it a wrong prompt, a prompt with wrong equations. We will feed it with 1 + 1 = 3, and check if it will output 3 + 3 = 7. And we will also save all these model internals of these two forward passes. So under the hood of this language model, you will see layers and attention and MLP connected in this way. And what we're going to do is use this patching technique. So how it works goes like this. Suppose we are interested in this orange node in this computation graph in this layer and at this position. We're going to copy and paste its value to the right-hand side. And it will override the model's original value here. And we will let this new value propagate to the output. And if by doing so, we find out that the model no longer outputs 7, it outputs 6 instead, we will get the conclusion that this node is really important for the model to do the +1 operation. And this is basically how activation patching works. It tells you what nodes are important in a computation graph. And we can go further by investigating what nodes influence the orange nodes we just found out. Let's say we are suspecting this red node is very important. And we can copy and paste it to the right-hand side and see how much influence it gives to the orange node, and see how much the orange node influences the output. And by doing this, we can just iteratively find what nodes are important and how they are connected. So in short, pass patching and activation patching are very effective techniques in interpretability research. And in this work, we are using them to identify attention heads and their interconnections that are responsible for outputting 7 instead of 6 for this particular prompt. And I'm going to skip a lot of details about applying this technique. This is not the main contribution of the paper. I'll go directly into the findings. So I'm expanding the view of this prompt, 1 plus 1 equals 3, and 3 plus 3 equals something. And by tracing how the model generates 7, we first find out a group of attention heads, which we will call group 1 heads, that are mainly in the last 2 layers of this language model. And also I'm showing their attention pattern here. They are mainly attending to the first to the token itself. So it's have this diagonal shape in their attention pattern. So the equation mark here will attend to equation mark. The 3 here will attend to 3, and likewise for other tokens. And by tracing this group of heads further back, we are going to find another group of heads, which we will call group 2 here. So for these group of heads, we will see, if we look at their attention pattern, we will see something periodical. For example, we see some highlights here. And these highlighted dots in the attention pattern actually means the model is attending to the in-context examples. So for example, at the position of the equation mark, it means this attention head is attending back to 3 in the previous in-context example. And we found many heads exhibiting the similar attention pattern. So collectively, we will call them group 2 heads. And lastly, we further trace what heads influence the group 2 heads, which leads us to the group 3 heads marked in green here. So these heads are having also a diagonal structure in their attention pattern, but it's slightly off the main diagonal. So meaning that these attention heads mainly attend to the equation mark from the in-context learning answer, like 3 here. So these 3 groups of heads work collaboratively to deliver the answer of 3 plus 3 equals 7 at the end of this computation graph. And this is what we find out about this model using this interpretability technique. And our next step is just to make sense out of these computation graph and these attention heads. So we need to make some hypotheses. So I want to bring up some of the early and important work in interpretability, which is called induction heads. So this is first discovered by the prior work in 2022. Some researchers discovered that there are a group of attention heads in language model that are responsible for the copying and pasting behavior. So language models will complete sequences like A, B, A by generating B as the next token. And this is achieved by using 2 groups of heads. One head is called previous token head, and one head is called induction head. So let's say a language model doesn't know my name, Qinyuan Ye. So when it first see this name, Qinyuan Ye studies NLP, it will kind of register that, okay, Qinyuan Ye is a name, and Qinyuan is the first name that appears before Ye, which is the last name. And later on, if my names appear again in the sequence, the model will probably use this induction head to retrieve what the information registered at the green head. So the next time the model sees my name, it will generate Ye as the correct next token instead of other last names. So this is an important finding from prior work. I'm bringing this up because I think what we found out about 3 plus 3 equals 7 draws a nice parallel to this previous finding. So on the right-hand side, I'm showing part of the result from our previous slide. And you can see that the structure of these heads look very similar to the left-hand side. So we can make hypotheses about how the model comes up with 3 plus 3 equals 7. My hypothesis goes like this. So perhaps when the model first sees 1 plus 1 equals something, the model is drafting the answer of 2 because 1 plus 1 equals 2 appear very frequently in the pre-training data. So the model will likely output 2 as the next token. However, the model sees the next token is 3 in the prompt. So this creates a conflict. And this is captured by the green head here, which will probably register the information that something is going on at the equation sign. And later on, when the model sees 3 plus 3, it will, in the beginning, try to generate next token as 6. However, the blue head here will likely to retrieve this information from the green head. And the green head says, okay, here I have the conflict of 2 and 3. There's likely an operation of plus 1. And this information is retrieved to the blue head, which will apply the plus 1 operation to 6, which will result to the output of 7. And this is a hypothesis we're making based on the past patching result we had on earlier slide, and also by drawing a parallel between the prior work of induction heads and so both these two sources leads to our hypothesis here. And I will also refer to the green heads as previous token head and the blue head as function induction head to draw the parallel between our work and prior work. And so far, this is a hypothesis, and I'm only saying this is one possible explanation here. And the rest of the paper is really trying to validate it with very extensive experiments. So to give a short conclusion to what we have so far, we hypothesize that language models may be implementing this function induction mechanism. This is a name we give to this finding. And it's very, one important thing we find out is that we think it generalized finding in prior work. And we also think it elevates it from token level to the function level because in the prior work, the induction had copy and paste tokens. But here, our function induction has copy and paste plus 1 functions. So that's like how we are different from this prior work. And I think I saw a question. Yeah, go ahead.
Can you unmute, Tim?
Yes. So my question is, does the PT head look at both previous tokens and the next token, right? Or it just look at the previous token?
So for the PT head, let me go to the earlier slides. So the green heads are the PT heads. Their attention pattern looks like this. So they are, so it means at this position, it look at the previous token here.
Yeah, I see. But my point is, does it contain the information of the next token or not? Like, do you have any hypothesis for that?
The next, which next token are you referring
For
to?
example, the break-in token or the next token after the break-in token, something like that. Does it contain the information of those tokens?
So maybe let's use this 1 plus 1 equals 3 as an example. Which one, which next token are you referring to?
So for example, you have plus 1 equal to 3, and then 2 plus 2 equal to 5. So my
Mhm.
point is, does the token 3 here can attend to the token 2 or token 5? Yeah.
So we are using auto-regressive language models. So that means 3 can only attend to things prior to it. So here we show 3 attends to equation mark. But later on, maybe 2 plus 2 equals 5. 5 may be able to attend to 3, but in fact, in our investigation, we find out that it attends to only to the equation mark.
Oh yeah, I see it. Thank you.
Okay, thank you. Any other questions? Okay, I'll go ahead and continue the talk. So we were here explaining our findings so far. And our goal next is to better understand and validate this finding. So there's one thing I'm curious about after figuring out this mechanism, which is are these blue heads in our hypothesis? These blue heads are writing out the function of +1, and in fact, we find out 9 different attention heads that are that fit this description and appear in these layers. So one natural question I'm having is, if 9 different attention heads are saying you should +1, why is it +1 at the end and not +9 at the end? So that's also one question that's triggering me to further investigating these blue heads. So in the next set of slides, I will introduce a set of experiments where we better understand these blue heads. So the methodology we adopt is also through patching and causal intervention. We will first run language models on a very naive prompt. For example, 2 equals 2, 3 equals something. And your model will likely output 3 with a very high probability. But then we will bring this back. This was our forward pass on 1 plus 1 equals 3, 3 plus 3 equals something. And we will bring out these computation graph and look at the function induction head, the blue head output, and try to copy and paste it to the right-hand side. So by patching it this way, and we might be able to see how this influenced the model's output. So for example, if beforehand we have 3 as the most likely next token, but by patching it, we see that there's a probability increase in 4, and then we will like conclude that, okay, this head is likely to be writing out the +1 function. So we do this for all the digits from 0 to 9. And this experiment will lead to heat map that look like this for each function induction head we just identified. And to read this heat map, let's take a look at maybe row 3. So this row is when input is 3. You will see that all cells except for the cell where output is 3 are all blue, meaning that there's a positive logic change. So this row basically says when the input is 3, all tokens other than 3 are promoted. They have higher logic values, and the token of 3 is suppressed. And if we look at the whole heat map together, it suggests that what this head is doing is that when the input is X, your X as output will be suppressed, but all other tokens are promoted. So this was what one of the blue heads is doing. And we do this for all the 9 different blue heads we identified. And this is what we find out. So we will see that each head have a very different pattern. And from this visual heat maps, we can also have some clue about what each of them is doing. So let's look at the first one. When the input is X, what this head is doing is that it's promoting +1 and +2. That's why you see a very dark strip here. And for the second heat map, it shows that the middle diagonal is suppressed, but the two diagonals around it, meaning X+1 or X-1, are promoted. And if you look at each of these heat map, like each of them is doing something special. Sometimes it's promoting like all digits greater than X. Sometimes it's suppressing things like X-1. And collectively, if we add up their effects together, these 9 heads collaboratively give us the X+1 function we are looking for. So the collaborative or aggregated effect of these 9 heads will look like this, where X is very suppressed and X+1 is very promoted. And this gives us the answer of how these 9 heads work collaboratively towards +1 instead of +9. Okay, I want to take a pause here for questions. Is there any questions so far? All right, I'll go ahead to the next part. So we now have a better understanding of how this mechanism works. But one limitation we have is we are focusing on a very narrow task called off-by-1 addition. And this is less ideal. I would love to see how the findings we identified can generalize to many different tasks and many different distribution of text maybe. So in the next part of the talk or the paper, I'm going to introduce like a different approach to see how this mechanism is reused in more broader settings. So the first thing we tried is, so far we've been focusing on off-by-1 addition. The offset is 1. What if we try different offsets like -1 or even 2, -2? In this case, your prompt will be something like 1 + 1 = 4, and you will be expecting your model to say 3 + 3 = maybe 8. And we investigate this with some head ablation experiments. Let's walk through the results together. So to read this figure, the top bars are representing the model performance with a base prompt. And that means we give the model standard addition prompt. And the red bar here shows the model's performance on standard addition. And the orange bar here shows the model performance on off-by-2 addition. And this just shows that when you give the model standard addition, it gets standard addition 100% of the time. In the next group of bars, we are presenting results when the model is given the off-by-2 prompt. So in the prompt, the model are given 1 + 1 = 4. We will see that models have non-trivial performance. They will output 3 + 3 = 8 in maybe 50% of the time. However, they have very low performance, outputting like the correct standard addition answer. So the next thing we did is we tried head ablation. We tried removing or disabling the 9 blue heads or function induction heads we identified earlier. And what we find out here is your model is no longer performing off-by-2 addition. By simply disabling these heads, your model goes back to performing standard addition. And to create a control group, we also tried ablating 9 random attention heads. and shows that this has very minimal effect on the model's performance on off-by-2 addition. So basically, the conclusion is that the same 9 heads we found about off-by-1 addition is also reused in off-by-2 addition. And we tried more offsets like -2 and -1. And our observations are pretty consistent. The overall conclusion is that when the blue heads, the function induction heads are present, the model performs off-by-k addition with non-trivial accuracy. But when these heads are removed, your model will go back to performing standard addition. That's why you're seeing 100% red bars in this row here in almost every settings. So the conclusion is that the same set of heads is reused for different offsets. It goes beyond off-by-1. It can go off-by-2, off-by-3. And the second thing we tried is, okay, we've been focusing on off-by-k addition, but we really want to see if it's reused more broadly. So we designed a task that is very different from off-by-2 or off-by-1 addition. Basically, we replace the first step in the task, which is standard addition, with a multiple choice QA question. And we replace the second step in the task with the shifting function of shifting the answer by 1. So every time you answer where the answer should be A, now the model is expected to output B, and where it should output B, it now is expected to output C. So we tried this out as well. These models are given like 5 shots of shifted answer, and to see whether their answer to the 6th question is also shifted. And we picked this subset from the MMLU dataset. And we also present the result with these bars in a way similar to the previous slides. So our finding is also consistent even with this very different task. So when you use the base prompt, meaning that the answers are not modified, our model can have a very good performance on this original task. But when you give it the shift by 1 answer letter, like A becomes B, B becomes C, it has non-trivial performance on this task represented by the orange bars. And when you further ablate these 9 heads we identified, the model goes back to performing standard MMLU, meaning that even when they're giving the wrong prompt, they give you the correct answers. So we've tried off-by-k addition, we've tried a shifted MMLU. In the paper, we tried more things. We tried other tasks like Caesar cipher and another task of base K addition. And in this talk, I'm going to give you a closer look at base 8 addition, which is one task we investigated and where the results are really interesting. So we took a closer look at base 8 addition, where we also find the function induction heads we identified are being really helpful here. So these are the prompts we were feeding to the model. This is one example. And I'm going to walk through some examples of base 8 addition. So for addition conducted in base 8, it's very different from the more commonly used base 10 addition. And it can be different in 3 different ways, which I'm going to highlight. So in the first case, it's possible that doing addition in base 8 and base 10 gives you the same answer. For example, here, 60 plus 16 in base 10 gives you 76. And this is also the result you will get in base 8. So there is also a second case where you might need to add 2 to the original answer in base 10, just because we are using a different base, so the computation is very different. So in this example, 13 plus 35 in base 10 is 48, but it becomes 50 in base 8. And in terms of the how you can arrive at the answer of base 8, it's possible to do this by just adding 2 to the unit digit and adding 1 to the 8th digit, meaning that 8 becomes 0 and 4 becomes 5. And there's a third case which is slightly different from the previous 2 cases. For example, 25 plus 16 in base 10 addition will be 41, but it will be 43 in base 8, meaning that you only need to add 2 to the unit digit, but you don't need to make any modification to the 8th digit. And you will see why I'm trying to describe base 8 addition in this way, because these add 2 and add 1 operation are exactly what these function induction heads were trying to do in the earlier slides. And this also partly explains why they are being helpful in conducting base 8 addition. So to look at this further, we generated 100 different test examples for each of these categories. So we have 100 test cases for case 1, and 100 for case 2, 100 for case 3. And we did the similar ablation experiments, meaning that when we disable the function induction heads, we find out that these models always perform base 10 addition. They don't do base 8 addition anymore. We also take a closer look at the error cases in each of these cases. And we find out that while models can apply +1 or +2 to achieve base 8 answer in some cases, these models do not always apply them under the right conditions. So sometimes they apply +2 when it's not needed, but sometimes they forget to apply it when it's actually needed. So it seems that when the model tried to understand the task of base 8 addition, the model is not like learning to do addition in base 8. It's trying to first do the base 10 addition and apply some of the shortcut solutions. For example, it learns to add 2, but it's still not figuring out when it should add 2 in a very accurate way. So this is one thing we find really interesting. The model may be like having performance gain on base 8 addition because of this mechanism, but it's not really grasping the real reasoning of the task. It's mainly learning some shortcut solution that gets you correct in some cases. Okay, I want to summarize the talk so far. So in this talk, we introduced how models perform off by 1 addition. And it's a very small, limited application, but we think it's very interesting to study, and it might help us answer many other important questions. So our work has 3 main findings. The first one is that we find out a complex function induction mechanism involving 3 different groups of attention heads. And we draw in parallel between our work and the prior work on copy-paste induction heads. To highlight that our work finds out something that works at a higher level, it works with functions instead of tokens. And secondly, we find out that these function induction heads work collaboratively. Each FI head we identified send out a very different unique fraction of the +1 function, and they add up together to the whole +1 function. And lastly, we try to see if this mechanism is reused more broadly, and we find that indeed they are reused in many different things, for example, off by K addition or shifted MMLU, or more interestingly, the case of base K addition. And these are the main conclusions from the talk. I have a few more slides before I end up the talk, but I want to pause here to see if there's any question.
So I have a question. Did you
Yeah.
also try it on quantized model and see how this affects or how this phenomena work in low bit quantization model?
Yes. So for me, I tried everything in their original model. I think they are like float 32. And I did find out that to apply the interpretability technique, if I use like float 16 models, I will end up getting in some numerical issues. So I would suspect that maybe these interpretability technique are very reliant on the precision of these numbers. So maybe I cannot do this with quantized models for now.
Correct, correct.
Okay, new question. Go ahead.
I have a question. Have you considered extending the study to other operations such as multiplication and division, or maybe perhaps questions like asking the model questions like, let's say, if you have 6 apples and eat one, how many are left? And perhaps getting the model to say 4 instead of 5.
So, do you mean by getting the model to say 4 instead of 5, is that still -1 instead of multiplication?
No. I'm asking, I'm suggesting 2 options. Have you considered extending the study to other operations such as multiplication or division? And the other suggestion is you could also try asking the same question, but in natural language format, like asking the model to say 4 instead of 5 when you ask a question like, if you have 6 apples and eat one, how many are left? So
Yeah, so for the first suggestion, I think I haven't tried multiplication division yet. And I think these will be interesting to do. But I will be very careful about the tokenization of these models. So I tried to use a very simple case because some of the models use like a 1-digit tokenization. That's how I'm able to do very controlled analysis without carrying over. But if we involve multiplication, there might be some like it's like less controlled. Sometimes it's 1 token,
yeah,
sometimes it will be 2
it's not
tokens.
as controlled. Yeah.
So
Right.
that's one concern I'm having right now. Now that you bring this up, but I think that's a very nice suggestion. I would like to see how this applies to maybe multiplication and other types of functions. And for the second suggestion, so that's indeed a very important limitation of our work so far. We just focus on like equations or very algorithmic task. We hope this is reused in natural text as well. So the example you bring up is really good example. We can take some math questions and see if these math questions expressed in natural language also triggers this mechanism. I just really nice suggestions. I haven't done them yet, but it will be interesting to do them.
Right. Sounds interesting.
Yeah,
Thank
thank you.
Yeah, I have a question.
Yeah, go
So,
ahead.
Um, uh, last time I have tried a dataset called object counting in Big Bench dataset, and the problem in that dataset is it can detect all the object and can generate the correct formula, but then the final answer is incorrect. For example, I can 1 plus 2 plus 3 equal to 4. So can we provide the model with correct example, correct demonstration, and then the model can output the correct answer? Do you think yeah, it can do that? Yeah.
So is your question suggesting that do you think in context like the correct demonstrations are going to help, or are you
Yeah,
do
yeah,
you want
right.
to
Yeah.
Yeah, I think um well, I don't work on this problem directly, so I can only make some guesses. My guess is your models nowadays should be able to do like 1 plus 2 plus 3 equals 6 correctly to a great extent. But in the case when they get wrong, usually they get wrong because maybe 4 and 6 are very close competitors in the output space. And sometimes giving them the in context learning examples will help you promote the correct answer of 6 instead of the wrong answer of 4. So I would say it it sounds that it's going to help.
Yeah, thank you.
Thank you. Hi, next question, please.
Can you hear me?
Yes.
Okay. Did you try like with the input prompt as like 1 plus 1 equals 3 and 2 plus 2 equals 4 and then see what happens with the next guess? Like with conflicting examples.
Okay. So are you suggesting that like some of them are correct, some of them are incorrect?
Yes.
I see. So I haven't tried this, but from my understanding of this mechanism, what it will do is that let's say let's say the next thing after 2 plus 2 equals 4 is 3 plus 3 equals something. And it's kind of 1 plus 1 equals 3 will kind of promote the models to plus 1. But 2 plus 2 equals 4 will kind of ask the model to keep its original answer. It's like two different forces trying to compete. So your model may be confused and hard to pick whether 3 plus 3 equals 6 or 7. And then maybe these two answers, due to the sampling or when we do argmax, the model picks one as the final answer. But I think under the hood, the model will be the two answers competing with each other.
Maybe thanks to the training data that they show like the correct examples, maybe the model will prefer the correct ones or not.
Yeah, it's also possible because 2 plus 2 equals 4 is closer to the next example. So models tend to give more importance to the closer one. And if that one is giving you the correct answer, then the next one will also give you the correct answer.
Okay, thank you.
Right, thanks. Any more questions? Okay, I have a few more slides. I'll try to finish them before the time limit. So remember that in the beginning of the talk, I was talking about how this is a very specific case, but it might help us answer some of the bigger questions. So now that we have answered to how models perform off-by-one addition, I want to revisit these questions and see if we can make hypotheses or speculations about them. So the first question I raised in the beginning is, can models really learn unseen tasks within context learning? And what we've seen so far in our study is that model seems to be able to compose two sub-steps together, meaning that if your unseen task can be viewed as a seen task and a simple function, maybe in the case of off by one addition, the first step is standard addition, the second step is +1. If this is the case, language model seems to be able to glue them together and infer this via in-context learning and apply it to the next example. So I guess this suggests that for a particular group of unseen tasks, we find some evidence that your model may be able to learn it. And this type of unseen task should be a combination of a seen task plus a simple transformation or function. And the second question I raised is, how do models handle misinformation? For example, 1 + 1 = 3. Our work suggests that, at least for models investigated in our work, they tend to not only follow this misinformation you give them in the prompt, they also generalize it to the next token prediction or the text that comes up next. So they not only believe 1 + 1 = 3, they also generalize it to 2 + 2 = 5, which I feel is quite concerning if this keeps going on. But luckily, there are the models investigating in our work are mostly like base language model. We just examine the pre-trained models. And for many models we interact with nowadays, people apply a lot of safety training to them. So this may be partially solved, but I feel it's still important to just learn how they happen in the first place. And last question I raised earlier is, why do emergent abilities emerge? This is also a question that I feel very interesting. I wanted to know about. From our work, I feel this is a very special case of emergent ability. And in this special case, we are dealing with a two-step task. And in our interpretability study, we also find out that early layers in the language model perform step 1, and late layers in the model perform step 2, meaning that larger models with more layers are more likely to have capacity to develop something in early layers and something in late layers. And contrasting with smaller models, they might not have enough layers to develop this structure. So that's some of my speculation on this question. And I also want to talk about two questions that may be interesting for future work. So something that comes to my mind is, how does this mechanism form during pre-training? How does the model learn such a flexible component during pre-training? And my personal thought is that this function induction head may evolve from the induction head we talked about earlier, and the function vector heads, which were discussed in another prior work. It's possible that this mechanism just take its basic form during the early stages of pre-training, but gradually evolve into its form today. And to validate this hypothesis, it will be very interesting to take maybe open models of today and take their intermediate checkpoints and examine this mechanism along their pre-trained trajectory and conduct a study similar to the work I'm showing here. And the second question that's inspired by our study is, I'm wondering how this function induction mechanism is reused in naturally occurring text. So far our work is really limited to synthetic tasks or algorithmic tasks. I think it will be very interesting to see how this is reused in the wild. So I think the question raised earlier has a very interesting idea of like having math problems but have a wrong answer. and these math problems are expressed in natural language. That's a good starting point. And also, I think it might be useful just to do a brute force search over certain text corpus, and by disabling this mechanism and see how, on what sentences our mechanism has a maximal impact. This will also help us identify how this mechanism is reused in natural text. And yeah, I think that wraps up my talk. Thanks everyone for joining. Let me know if you have any more questions. Thanks.
Wonderful session.
Yeah, thank you so much. The slide is not public yet. Yesterday I was still updating it, but I will try to upload it and maybe send it to my website and try to post it somewhere. Thanks.
I have a question. So,
Yeah.
what do you think is the impact of the data selection that was done in these models, like the pre-training data? So, like we are calling these unseen tasks, but because the data is private, we don't really for sure know that if there are similar examples that have caused models to learn and function induction type like this.
Yes, that's a great question, and we had this concern as well. So something we tried is to search in some of the open corpus whether examples of off by one addition exist. So we find very small number of occurrences of these. And for example, we know like 2 + 2 = 5 is sometimes used in literature to express maybe sarcasm or something. These are indeed in the pre-trained corpus, but not like in a task that looks like off by one addition. So that's what we found out about in open corpus. It's possible that in these proprietary data, there's something that like this. So we cannot confirm or deny its existence because that's not public to us. That's also why I think like reinvestigating this with open models trained with open recipe will be a meaningful contribution.
Right. And there is an difference between a base model and a model that is like trained for reasoning or SFT, RLHF. So will there be a difference in how both of models behave for these types of tasks?
Yeah, I don't have concrete answer for this, except that I tried the 1 + 1 = 3 and 2 + 2 = 5 model on a post-trained Llama 3 model. It also gives me 5. So I think this is still partly present in these post-trained models. Yeah. Other than that, I don't have conclusions. I hope these post-training procedures can solve maybe how models handle misinformation or issues like this. Okay, I see another question in the chat. So Ting said reasoning models do not have the in-context learning ability anymore. Do you think if it's worth continuing discovering induction heads, function heads, etc.? Yeah, so I feel reasoning models, I'm not sure why, but maybe reasoning maybe in context learning is no longer the priority for reasoning model, so it's not like highlighted or weighted highly in the training data. But I guess for me personally, I just feel it's important to understand in context learning abilities, just how it emerged, and help in understanding the mechanism under the hood. So I think it's still worthwhile to study these properties. And I think they will still be reused maybe in some less obvious ways. Maybe when you interact with a reasoning model, you give it some misinformation, or maybe you give it 1 + 1 = 3 as a prompt. Maybe we can help, or maybe this mechanism can help answer why these models, or how these models may be affected by your prompt. I think these are like some of the practical implications I can think of for reasoning models. But honestly, I feel like studying it with the context of the base models, non-reasoning models, is also very interesting by itself. Right, I see some discussion in the chat. Reasoning models seem to implicitly rely on ICL to push forward their reasoning. Yeah, that's a very nice explanation as well.
If we don't have any other question, we can conclude the session. Thank you so much for the amazing talk. So we have one more question.
Okay, let me take this last question. How hard was it to find the functional heads? How much time did it take? So what we did is, let's go back to this slide. So what we did is we kind of enumerate these heads. Let's say to find this orange head, we need to enumerate all the heads in the language model. And that procedure probably takes 2 hours to run. And it takes more time to further see like what heads further influence the orange head. So that procedure takes a lot more hours. I hope that answers your question. And that's also dependent on the model size. If you have larger models, it takes longer. So yeah.